this video, I want to revisit an example that I examined in my last example video, and I solved the problem that time using general planar motion. This time I want to solve the same problem, but I'm going to make use of the instantaneous centers of rotation principle in order to solve it. So the problem I'm revisiting here is the problem where we have a piston driven within a cylinder. There's a connecting rod and a crankshaft, and we know some stuff about the crankshaft, the orientation, and its rotational velocity. Ultimately, what we're trying to find then is the piston velocity over here. So to do this, I'm going to examine the connecting rod, which connects B and C here, because it contains useful information in that it's connected to my crankshaft, which I know some stuff about, and specifically its rotational speed, and it's connected to my piston, which is what I'm trying to solve for. So it's a useful thing to start with. So I'm going to try to draw my connecting rod out here in a little bit blown up fashion to give myself more room, and label my ends B and C, and recall that I know that the velocity of B is related to the rotational velocity of my crankshaft. So previously we had solved for this, but just a little bit of a rehash. We did a little unit conversion to find the rotational velocity of the crankshaft as 209.4 radians per second. And then from that, since this is just an object rotating, a fixed axis rotation, VB out here like this, we can solve for VB using the length of that crankshaft, which is 3 inches, and we get 628.3 inches per second. So that is our solution for VB here. Next, or ultimately what we're trying to find then, is the velocity of the piston, which we're calling VC. Now, from an instantaneous centers perspective, the things that we know are that our instantaneous center must lie on the line that is perpendicular to my two velocity vectors. So it must be located there. And realize I have a point labeled C already, so I'm going to call this IC. Now, from the last time I approached this problem, we had already solved from some of the geometry. So rather than, again, re-solve that, which we can refer to the previous video, I'm going to bring some of that geometry in here. To use in this problem. So what we know then is that we have a triangle with these given angles, and we know the direction of our vectors, again based on our geometry from the problem setup, and we want to be able to solve for VC. So since this is just a triangle with some arbitrary angles, I'm going to use the law of sines and solve for some of my side lengths here. So the one side length that I know is that BC, the connecting rod here, is 8 inches in length. And then I know that that must be equal to the sines of each of the angles divided by their corresponding lengths, which I'm just going to label with the labels for these points. And I can solve each of these by rearranging and solving for these lengths, and I get that the first one here, CIC, is 8.44 inches, and BIC is 10.14 inches from these equations. Now, what I've got then is a fully specified triangle. And ultimately, again, what I'm trying to find is this velocity VC. And from instantaneous centers, what we know is that the rotational velocity of this arm around the instantaneous center must be equal to the velocity at any point perpendicular multiplied by the perpendicular distance back to the instantaneous center. So from that information, I can solve, giving myself a little white space here, I can solve first for the rotational velocity of the connecting rod because I know VB. So if I plug in my knowns, I end up with 61.96 radians per second. Now, this rotational velocity is true for any point, or true as a corresponding rotational velocity for any point located on this rigid body. And of course, the one that I'm interested in is point C. So I can use it then to solve for point C by plugging in to this equation. And I get from this an answer that looks something like that. Now, my number here is a very slight bit off from the previous time I solved this problem. Mostly that's just due to some rounding and stuff in my calculations. It's not off by very much. So using instantaneous centers, we were able to approach this problem in a slightly different way and get effectively the same answer. All right, thank you.